Welcome to another video, and today we're doing a quick benchmark of some Arduino compatible boards using the Dhrystone and CoreMark benchmark tools. Dhrystone is a synthetic benchmark which only uses integers in its calculations to give a view of performance of different programming languages and hardware. The results are reported in VAX MIPS from this sketch, where MIPS is millions of instructions per second, and then the VAX value is calculated by dividing this by 1757. To perform these tests, we simply loaded the Dhrystone benchmark sketch by Gareth Harvacree into Visual Micro, and then uploaded it to each board in turn, and then charted the data shown from the serial monitor in Excel. Note, we've had to increase the number of iterations to 12 million to make this useful across all of the boards we tested. Otherwise, some boards resulted in an error where the measured time is too small to obtain meaningful results. We also ran this for different clock speeds where these are available on boards such as the ESP32, the Raspberry Pi Pico, and the Teensy 3.6 and 4.1. We can clearly see the boards with the best performance on this benchmark are the Teensy 4.1 and then the Portenta M7 core being the next closest. To have a fairer comparison, we also calculated the MIPS per megahertz, with this chart being in the same order of boards as the previous one. Again, we see that the Teensy 3.6 and 4.1 boards give the best performance, and the ESP32C3 also sticks out above the baseline, with the Nano 33 BLE being next. We've also run these benchmarks with the more up-to-date CoreMark tool, which is a newer generation of benchmark for embedded devices. The results shown here are in the same order of boards as the other charts, and as we can see, this is virtually identical to the original MIPS chart, with some minor differences between some of the boards in their scoring due to the different measures used to calculate the score. CoreMark is also available on GitHub, and the example project for Visual Micro is also linked on the page in the description, along with all of the charts shown in this video. We know there's a lot more to embedded devices than just raw power. However, being able to perform very complex calculations quickly is paramount in some embedded applications. For example, determining where a noise came from using a set of microphones as inputs, which requires a lot of complex and heavyweight mathematical calculations. The data from this video is also available on the page in the description, and we hope this information is useful to you. Don't forget to like and subscribe if you enjoyed this video, and don't forget to check out the other videos on our channel.